everyone. Welcome to my living room once again for our next lecture. Okay, so we're going to start a new topic today. So today is lecture number 24. We are now on chapter number 13. We're going to cover stuff that is on pages 336 to 352. No specific readings for next class. And your homework, your first homework since we switched over to this new format, will be due on Monday, okay? At the same time that we would usually be having class. Today we're going to introduce gravity. And we are going to talk a bit, just a little bit, about orbits. Okay. So, of course we've been talking about gravity up until now, right? We've been talking about there's objects and gravity exerts some acceleration on them. Technically, of course, there's a force that's exerted on them which causes an acceleration of 9.81 meters per second squared, pointing straight down. So, if we're here, in our little house, and there's a little tree outside, gravity looks like it's always pointing down. Right? And no matter where we go around, we're very large compared to our house and tree. No matter where we go, we see this same force, right? We don't go on the other side of the house and then gravity's pointing this way, and we don't get up into the roof, the attic of our apartment and find that gravity is much weaker, or go into the basement and find that it's much stronger. But this simplification that gravity is this constant force that always points directly down towards our feet is of course not entirely correct. As you know, if we zoom way out, and of course I'm not going to be drawing this to scale, but here's our little house, here's a little tree, here's us. If we zoom way out, we see that gravity doesn't point directly down anymore. Where it points is towards the center of mass of the entire Earth. Right, so if the center of mass of the Earth is somewhere roughly in the middle, we're going to have this gravitational force pointing in towards that center of mass. So the direction of the direction of the force of gravity is not constant, but changes as we go around on this circle. Not only that, but as we get further out, that force of gravity gets weaker and weaker and weaker. So if we get in a spaceship and we go very far from Earth, the gravitational attraction to the Earth gets weaker and weaker and weaker as we go further and further out. So the discovery of gravity, like most of the things we study in this class, is due to Isaac Newton. And Isaac Newton was searching for the answer of why do the lights in the sky, the planets, follow these particular paths that they do? What rules their motion? So there was a lot that was known about the mechanics of orbits before Isaac Newton came up with the exact mathematical explanation, and we'll get to that either towards the end of this class or the beginning of next class. But these empirical laws that were derived just by looking at the planets and seeing how they moved gave us mathematical laws, but it wasn't until Newton came along that we were able to find the explanation for these mathematical laws. Why, from first principles, are we able to find that orbits follow these specific mathematical laws, which are called Kepler's laws. Okay, we'll get to that in a little bit. But what Newton was able to figure out was that the force of gravity, the same thing that causes stuff to drop on the Earth, right, is the same thing that causes these planets to move around on their orbits. So think for a little bit about what a revolutionary idea that was, right? There are two different types of phenomena that we're looking at. We're looking at phenomenon of lights in the sky moving according to particular patterns, and we're looking at things on the Earth, falling or dropping just excuse myself for missing it. My cat is now very excited that things are moving and dropping. So why should these two phenomena be related? It was Newton's insight that allowed him to see that these two things were happening for the same reason, which is the force of gravity. Right, I suppose half of you are thinking the cat showed up, the other half are like, oh God, please show us your cat. So here's my cat. Here's Franz Josef von Habsburg. He's a very sweet little kitty. Yeah. Okay. Where were we? So when you hear that story of Newton sitting under the apple tree and the apple hits him and he thinks, haha, gravity. It may seem like a strange story, right? Because what did he just then realize gravity exists? No, well his insight was that, the story goes that he was thinking about orbits, right? These celestial mechanics, the way things move around in the sky, and then that's when the apple hit him and he realized the connection between those things that he was thinking about and the phenomenon of gravity that we have here on Earth. Okay? So, before we get into celestial mechanics and orbits and stuff like that, let's just write down Newton's law for gravity to start off with. So the force of gravity, which itself, of course, is a vector, between two objects, A and B, is equal to negative G MA MB divided by RAB squared. And I'm going to put in a unit vector that points from A to B. Okay? So that unit vector, if we wanted to define that more concretely, AB, that would be the full vector that points between two objects divided by the absolute value of that vector. So this guy just points along the direction between two objects. It can get kind of confusing thinking about this negative sign and this AB and which order they go in, but there's an easy way to think about it, right? If I have an object A and object B, which are large enough that we can notice their gravitational attraction to one another, well, I know that the force of gravity is always going to be pointing towards the other object. So this negative sign is just telling you it's pointing in the opposite direction of the vector that points between those two objects. So if this is my vector RAB, right, then my unit vector, of course, points along that same direction. And the force of gravitation is in the opposite direction of that vector, right? So the force of B on A is going to be pointing in this direction here, right? So this negative sign is telling us gravity is always working inwards, towards the other object. So it can get sort of confusing thinking about these unit vectors and this negative sign and stuff like that. But most of the time it's going to be pretty clear which direction the force of gravity is going to point in, right? So this is the formal definition, but we're going to be a bit loose with it because we know that gravity is always attractive, so every object attracts every other object according to gravity. Okay, so there's a few things to talk about in this equation, right, other than the confusing negative sign and the confusing unit vector. One is that the force of gravity is 1 over r squared, right, where that r is the distance between those two objects. So what this means is that gravity is at its strongest when the two objects are physically close to one another. And as we move those two objects apart, the force of gravity gets, of course, weaker and weaker and weaker. It never goes to 0, right? Which means that every object in the universe gravitationally attracts every other object in the universe. So you are right now feeling the gravitational attraction from, a planet out on the other side of the galaxy is still exerting some force on you. It's just that because that distance is so large and we're dividing the force of gravity by, or rather when we calculate the force of gravity, we use 1 over r squared according to the distance. That distance is so large that this force of gravity gets so small that we don't notice it anymore, right? Every atom in our body feels the gravitational force of every other atom in the universe, but most of the time you don't notice it because these distances are so great, and 1 over r squared dividing by that gives us a very small number. Okay? the thing that controls how strong gravity is between the two objects is the mass of those two objects. So we feel the gravitational attraction of the Earth because the mass of the Earth is incredibly, incredibly large. Right? We also exert that same force back on the Earth, right? Because if I switch MA and AB, right, I get the same numbers. Okay? I'm just multiplying them in a different order. So there's a reciprocation between the forces of gravity, right? As the Earth exerts a gravitational pull on me, I also exert a gravitational pull on the Earth. It's just that the Earth is so much more massive than I am and so much more difficult to move that, of course, we don't notice that movement. The other salient feature of this equation is this G there. So that G is what's called the universal gravitational constant. Or more frequently, just big G. Its rap name is Big G. I'm assuming you've laughed at my joke. Okay. So this big G tells us how strong the gravitational force is, right? This is a physical constant that, in a sense, controls how powerful the gravitational force is. If we were talking about electrostatic attraction, electromagnetics, we would have actually this same equation, but with different letters, right? And one of those different letters would be, we'd have a constant here instead of G. And we would have the same formative equation, but with different numbers plugged in. So this G tells us we're working with gravity, right? And it's called big G, of course, to contrast it with little g, the 9.81 meters per second squared acceleration of gravity near the Earth's surface that we always feel. Okay. So this big G, despite its name, is really, really small numerically. So G is 6.67 times 10 to the negative 11 Newton meters squared over kilogram squared. So you may remember these units from that problem we did in dimensional analysis towards the beginning of the semester. But now we're getting this actual number, which is 0 point and then 10 zeros, 667. Okay, so this number is really, really tiny, and that tells us that the force of gravity is extraordinarily weak. Okay, you may think, well, how is the force of gravity so weak, right? It's the thing that holds solar systems together, the thing that holds a star together, holds us to the Earth. You might think at first thought that it's a very strong force, but if we compare it to the other forces, we can see that it's very, very weak. Okay, so do I have a magnet? Yes. From my fridge. So if I've got this pink magnet there in my hand, right? What's holding that magnet to my hand? Well, my hand's in the way, but really what's holding it there is the force of gravity of the entire Earth. So the mass of the entire Earth is generating the gravitational field that holds this magnet in the palm of my hand, right? There's a force pushing down on it. If I take another magnet, which is very small compared to the Earth, I can easily pick up that other magnet, okay? Which means that the magnetic field generated by this magnet is overpowering the gravitational field generated by the entire Earth. So this number is so small, and this means that the force of gravity is so weak. Okay. So gravity is one of 4 fundamental forces that make up the universe. There is, in descending order of strength, there is the strong nuclear force. The strong nuclear force is the thing that holds the nucleons together inside the nucleus, that binds together the protons and neutrons inside the nucleus of an atom that holds a nucleus together, right? If you've ever thought about the nucleus of an atom, and you know that it's composed of protons and neutrons densely packed together, you might think, well, how can it be that two positively charged particles are held together even though we know that particles of the same charge repel each other? Right? Positive repels positive, negative repels negative. It's only positive and negative that feel an attractive force. So if there's nothing negatively charged in the nucleus, what sticks it together? Well, indeed, these particles are repelled by the electrostatic force between them, but the electrostatic force is not nearly as strong as the strong nuclear force, which overpowers that electrostatic force and binds the nucleus together. Right? And then we have the weak nuclear force, which really only comes up in very specific situations related to particle physics and doesn't play much role in mechanics. Next we have electricity and magnetism, the electromagnetic forces, which are quite strong, but not as strong as the nuclear forces. And then we have gravity, which is by far the weakest force. Okay? Any force that exists in nature is one or more of these forces. Okay? You may think, well, what about the force of just things being in contact, the contact force, or normal force, right? Well, if I zoom into my hands, way in, okay, until I get down to the level of the individual atoms, I will see that the atoms themselves are distant from each other. And if I look inside the atom, the overwhelming majority of the space inside an atom is actually just empty space. Okay? The actual physical stuff of the particles, whatever that might be, is very small compared to the distances between the particles and the atom. Right? So when you believe that you're pushing up against some solid object, really what you're doing is feeling the electrostatic repulsion between the atoms at the surfaces of your hand, right? That's actually, it's not two things coming physically in contact with each other, right? It's the electrostatic force repelling them at those short distances. So you'll get to electromagnetics. Hey, stop that. Cat's messing with my stuff. Hey. Where was I? That. So let's look at how the force of gravity acts on an object on the Earth. So force of gravity. Oh, my cat's messing with stuff. Right back. Okay, sorry about that. Last thing I need right now is my cat eating a magnet. So force of gravity on the Earth is G M R radius Earth squared. Okay, so this circle with a cross in it, that's the astronomical symbol for Earth. Okay, so the force of gravity at the Earth's surface is equal to G, mass of the Earth, the mass of the thing feeling the Earth's gravitational force, and divided by the radius of the Earth squared, right? We're all standing more or less at the Earth's surface, so any small variation, right, whether we're up on a mountain or down in a valley, you're not really going to see that because this radius of the Earth is so big. Okay. So we know from Newton, force equals mass times acceleration. So force of gravity is equal to mass times acceleration due to gravity. And so we just plug that in here. Mass gravity, gravity, mass, radius squared. Okay, the first thing you'll notice is that I can cancel out the masses of the objects that feel the force of the gravity of the Earth, right? So this is why all objects fall at the same rate in the Earth's gravitational field, is because we have this kind of cancellation. What type of object we're talking about doesn't matter, because whatever that object is, I have mass on either side, and it always just cancels out. Okay. So then if we plug in these numbers, actually, sorry, I was looking at two different lines in my notes at the same time. So we took Newton's equation for gravity, for the force of gravity. First we showed that we can cancel out the mass of the object itself. And then we've got stuff that, even back in Newton's time, they might have known. Well, they might not have known this number here. In fact, they didn't. But what we get out of this, right, we plug in what we can measure for the gravitational acceleration of the Earth's surface, right, the rate at which that happens, the radius of the Earth, okay, and this is something that Newton did roughly know. The radius of the Earth was known even by the ancient Greeks, who were able to find geometrically the radius of the Earth and the distance from the Earth to the Moon by geometrical arguments. Right? Universal gravitational constant. Okay? And then we can solve that equation for the mass of the Earth. So if I am able to calculate, or rather if I'm able to find this universal gravitational constant, I can weigh the Earth, right? I can find out how much the Earth weighs. And that's what they called it the first time that the universal gravitational constant was measured accurately for the first time. They called that experiment weighing the Earth, because you could then find that the Earth is 5.97 times 10 to the 24 kilograms, right? So essentially 6 with 24 zeros after a kilogram. So obviously the Earth is quite massive. Okay? Not compared to the Sun. The Sun is about 10 to the 30 kilograms, 1.9 times 10 to the 30th kilograms. Okay. So the next natural question would be, well, if I can find the value for big G and find the mass of the Earth, well, how do I go about finding the value for big G? And the way this is done here, I'm going to squint at the time. Okay. The way this is done is with something called the Cavendish experiment. So what is the Cavendish experiment? I will draw and then explain. So the Cavendish experiment uses something called a torsion pendulum. If I were in class, I would grab a meter stick to demonstrate a torsion pendulum. Hold on. I made a torsion pendulum. Aren't I crafty? Okay, so what's a torsion pendulum? You're used to a regular pendulum that just sort of swings back and forth like that, but a torsion pendulum doesn't do that. Okay, so a torsion pendulum, instead of swinging back and forth, like so, twists. Oh, it's about to fall apart. It's a very poorly made torsion pendulum. There's no reason for you to watch me do this. Okay, we're back. So, the torsion pendulum, instead of swinging back and forth like so, twists. So it twists. Let's see if I can get it to actually work. So it goes in one direction, and then it starts swinging back around the other direction. And then that rope twists up a little bit, or string rather, and it twists around the other direction. So instead of going back and forth like this, it goes like this. Right? The restoring force for a regular pendulum, the thing that keeps it in motion, is that this periodic interchange between gravitational potential energy here, kinetic energy, gravitational potential, kinetic, gravitational potential, kinetic. Here, for the torsion, I have kinetic energy, and then what I'm doing is I'm storing potential energy in the twisting of this string, which is torsion. Torsion is to twist, right? Torque, torsion, twist. So that elastic, essentially, potential energy gets stored up and then back this way, and back and back. So elastic potential, kinetic, elastic potential, and on and on and on. Okay, so why do this? Well, we want some sort of regular process that is happening perpendicular, right, like so, to the force of gravity of the Earth. Okay, so the force of gravity of the Earth is perpendicular to the motion of this torsion pendulum, so it doesn't affect it. Okay? So, what Cavendish did, now where did I put my marker? Oh. What Cavendish did was make this torsion pendulum, and at either side of it, there is a small mass. Okay? And to either side of that, each of those small masses, there's a large mass. Okay? So you build this, you set it up like this, and you let it come to rest. Now when it's at rest, you have the situation where the force of the torsion pendulum wants it to start twisting this way, but the gravitational attraction between this large mass and this small mass is enough to cancel out that attraction, or rather that torsion force that wants to push, or rather wants this thing to twist this way. It's attracted back towards the masses. So if this is in a stable configuration, those two forces have exactly canceled out. Now what you do is you take this mass, move it real quickly over here. You take this mass, move it real quickly over here. And now, the gravitational force between these two balls here, is pointing in the same direction that the torsion pendulum wants this bar to twist in. Right? So now this thing's going to accelerate. It's going to start moving. And I know that half of that motion is going to be due to the elastic potential energy, the torsion, and half of it's going to be due to gravitational attraction between these two objects here. So when they move, when they accelerate, if we measure the acceleration, angular acceleration of that thing as it moves, we can find out what the force is, and therefore we can find out that big G, because these two masses are now known. Okay? Why all this complication? Well, if we were to do it just in the thing we did on the last board, right, we would have to know the mass of the Earth. But if we didn't know the mass of the Earth, which people didn't originally, then you could find the gravitational force between these two objects, right? And we could do that because it's moving through a direction that's perpendicular to the Earth's gravitational field, so that's not interfering with the experiment. Okay? So when this experiment was performed for the first time, that was called weighing the Earth. It's interesting to point out maybe that we don't have much better estimations of big G now than when Cavendish did this experiment. Because the gravitational force is so minuscule, it's very difficult to measure, and of course now we can do more accurate versions of this experiment, but we're sort of stuck with this same sort of thing, right? That Cavendish's original experiment, pretty close to the value that we have now for big G. I'm not sure how the most accurate measurements, modern measurements of big G are done. It might be interesting to look into. Okay, how am I doing on time? Oh, plenty of time, okay. So let's do one other sort of quick calculation. So how can we prove that the force of gravity is the thing that holds the moon in its orbit around the Earth, the thing that holds the planets on their orbit around the sun, and the sun's orbit around the center of the galaxy? Okay. How do we know that all these celestial motions are really due to the force of gravity? Well,